on the beach. And before we get into our project. Oh, I'm Katie. Sorry.
I'm Bobby.
Nicole. Okay. So now, our project is going to be back on the beach, and we're kind of doing it as a story. So we're going to start with the history of the map that we're going to use. First, we're going to start with history of finding the area under a curve. And integration originally began with finding the area under curves. Cavalieri was an Italian mathematician whose work focused around the observation that a curve can be sketched by a moving line considered to be sketched by a moving point, and an area can be sketched by a moving line. And so he discovered indivisibles. They're all the infinite points on a curve, and he also discovered that a moving point can be considered to sketch a curve where the sum of all the indivisibles is equal to the curve, and is visible. Indivisibles of area is the infinite number of lines that are equal to the area under a curve. He was also the first to consider geometric figures in terms of computation of the area. And then, major breakthrough to understanding integrals was when Cavalieri used his knowledge of indivisibles to imagine there were an infinite number of shaded regions. And so the shaded areas became as small as a line, and you can see on this graph as they increase, that it gets closer and closer to the curve, and the jagged steps of all the lines would be small enough to become the curve. As the jagged steps form a line, the shape becomes so as they get smaller, you get a full curve. And then we move into the histories of integrals. And Charlie and Brady touched on this too. Archimedes and Exodus found formulas for the surface areas and volumes of solids such as cones, spheres, and cubes. And then Newton and Leibniz just developed the fundamental theorem of calculus, which is the main idea that differentiation and integration depend on each other. And then Gauss made the first table of integrals, and as it continued to develop, before the 20th century, over 27 scientists and mathematicians worked on integral tables and developing integration.
So for the history of the beach portion, rather than the math, we did a little timeline of scuba diving to start out. So the ancient swimmers cut hollow reeds to breathe, which they used as a snorkel. So obviously they couldn't go very deep into the water, because as soon as you're snorkeling under the water, you no longer can breathe. The Persian divers created highly polished helmets out of turtle shells, so they could get even deeper under the water. And then in 1771, John Smeaton was the first to create a scuba diving gear that you could actually breathe while underwater. He invented a pump, which was a hose that the diving barrel would pump the air back to the package on your back. Smear-Fimray invented a rebreathing device that recycled the air of the pump on your back in 1972, but the users of this quickly died from lack of oxygen because you were breathing in the carbon dioxide you gave back to yourself. Henry Fluess in 1876 invented an oxygen rebreather. He died from excessive oxygen because he had too much oxygen because that's all he was giving himself. And then Vigneault, Recoil, and Auguste Denrose finally built a suit that was safe enough to be used by people in 1873. Unfortunately, this suit weighed over 200 pounds, so there wasn't a whole lot of swimming going on while they were swimming. Emile Gagnon and Jacques Cousteau, they invented the modern breathing regulator, which improved the old diving suit, so it no longer weighed 200 pounds and you were able to swim around with it on. In 1942, they also created a regulator that automatically refreshed the air each time the diver took a breath. So as part of our story, we're going to Lake Saginaga. So some history behind that is it was the Voyageurs Highway in the 1700s, and Voyageurs were the name given to the boatmen who were employed by the fur companies to bring their goods back and forth. It compromises in 4 parts in Canada and the United States, which means that it touches land in 4 different national parks. And then it's a major trading post, and it was one of the 3 major ones used by both voyagers and Native Americans. History of canoes, it was developed by Native Americans, which can't exactly be pinpointed, just we know that they were using them when we came over. First used by people of the Caribbean to travel between islands. It originated from kinu, which means dugout, and it's more commonly used by Native Americans and fur traders originally.
Alright, so here we go. The 4 of us get together, we call each other up, and we decide we want to take a trip. We want to go to the lake and we want to get on a canoe, or ride a canoe in the lake. So we get together. Paige starts it off with a group message. I have an Android, so I didn't get it at first. There's some updates with my phone, I get group messaging, we're good. So it's a 5-hour drive actually, or that's how long it takes us. Nicole was driving, it was supposed to only be 3 hours, but we get lost. It's okay, we're having a great time, we stop and get some food. We're playing I Spy Slope Fields. We're playing rock, paper, pie. We're just having so much fun. So we get to the lake, and we get our canoe, which we brought with us. We made it ourselves. Our canoe is 10 feet deep. All right, it's 2 stories. We are excited. We start paddling. We start paddling in the canoe. I'm not really paddling. I'm just kind of taking it easy. But we're going into the middle of the lake, which is 500 feet in. All right, and out of nowhere, there's this huge wave. There's a storm coming in, and we are terrified. But we want to know what is the average height of this wave along what is the maximum height. Now the wave represents the function of f of x equals 5 times 1 plus the cosine of x. And it's on the interval of negative pi to pi. So we find the average height by integrating negative pi to pi of f of x and then multiplying it by 1 over 2 pi. From this, we find that the average height of the wave is 5 feet tall. But we also find that the maximum height of the wave is 10 feet by using our calculators, which we brought with us, and graphing it. So 10 feet, so it's exactly the same size as our boat. So we're scared that our boat's gonna tip over and we didn't bring life jackets. That's the trick of so we're scarier. So the wave actually crashes into our canoe and we're wondering, what are we gonna do? And out of nowhere, we see that there's water coming into the canoe because we have a hole.
This hole is bringing in water this hole is bringing in water, and we want to know how many gallons the canoe can hold, so we need to know how much time that we have to get out of the boat. The bottom of the boat represents the function f of x equals x squared minus 4 over 4, which is this curve right here, and then the top of the boat equals the line y equals 9. So we find the points of intersection by using our calculators, and we find that they are at 6.324555 and then negative 6.324555. So we integrate the function, we subtract the function 9 minus x squared minus 4 over 4, and then we integrate from the points of intersection, and we find that the boat can hold 84.327 cubic feet of water, which we don't really know how much water that is because we don't use that. So we need to convert it to gallons, and 7.48 gallons equals 1 cubic foot. So we find that the canoe can hold 630 approximately gallons of water.
All right, so as our boat can withstand a lot of water, we are still really scared. Like, we just want to get out of here. I want to go home. So we didn't bring a life jacket, but we brought a flare, one flare. So we got one shot at this. Now, we see in the distance there are these 40-foot trees. So we want to make sure that our flare is able to get over those 40-foot trees so we can get some help. So we know that our initial velocity of the flare is going to be 0, and the initial height of the flare is going to be 0 as well. And we know that our velocity function for the flare equals, or is the same as y equals negative 8t plus 32. So we set the velocity function equal to 0 to find the possible critical numbers. And we find that there may be a critical number at t equals 4, at the same time, we also find the antiderivative to find the position function, which we find to be y equals -4t squared plus 32t plus 0, because 0 is our initial height. And then using the two intervals from 0 to 4 and 4 to infinity, which we found to be our number, our possible critical number, we plugged in values into, or intervals into those range, into our velocity function, and found that t equals 4 is the relative maximum because it changes from increasing to decreasing at that interval. So once we found that, we used the position function and plugged t equals 4 into that to find the relative, or to find the max at time equals 4. And we find it to be 64 feet. So thus, minus the 40 from the 64, our flare will reach 24 feet above the trees. So we're really excited about that.
So now our boat is completely capsized and we are stuck in the middle of the lake with nowhere to go. So we decide we're gonna go scuba diving. So we put on all of our gear.
We put on our life jackets, we brought the scuba gear.
Oh, and in case you were wondering about the flare, I tried to light it. It didn't work.
Wrong person to choose for that.
Yeah.
So
Thank you, Katie.
we get on all our gear and we realize we only have one light underwater in this super deep, dark lake. And we need to know if we can make it to the shore with only one light, if we'll all be able to see if we're gonna crash into each other and die because of the oxygen. So we figure that the light beam is in the shape of a cone, and we know that 3 feet under the water, it has a radius of 1.5 feet, and we know the total depth of the lake can go 20 feet down below the surface of the water. So we set up a ratio that combines 3 over 1.5 to 20 over the radius at the very bottom of the light beam. And we figure out that the largest radius the light beam can have is 10 feet. So then we plug it into the volume formula and we find that the light beam has a total volume of 2,094 feet. So therefore, we can all see it and make it back to the shore safely. Thank goodness.
So, through this process of not dying on our trip, you can see that we ended up using integrals, finding the area under a curve, and then